So today we have to study about moment of inertia. So first of all, we need to focus on this word inertia. It is a property of a body by virtue of which it remains in the same state in which it actually is. What I mean to say is that if body is in the state of rest, it will remain in the state of rest. And if body is in the state of motion, then it will remain in the state of motion. So this is the physical meaning of moment of inertia. But as per our curriculum, we have to study, or we have to evaluate the moment of inertias of different bodies having different shapes. So in vector notation, if I see what actually moment of inertia is, so it is I n cap. N cap is a unit vector. I will discuss about it later. It is equal to summation I mi n cap cross ri square. Here I is the moment of inertia, n cap is the axis about which we have to calculate moment of inertia. Now since we are discussing about continuous bodies, though sometimes because bodies are of arbitrary shape, so it is difficult to find the moment of inertia of a whole body once. So what actually we do is we chose a small part, or we choose a small element mi. Furthermore, I can write it as dm also, small element mi. Then we find moment of inertia of small part mi, and we summarize it, or we add all the parts. Ri is the position vector from the origin. This is for the case of discrete bodies. And if I have to discuss about continuous bodies, then the moment of inertia I along the axis n cap, it will be represented as n cap cross r absolute square dm, where dm is the small mass element. Means if I need to calculate the moment of inertia of this whole body, I will not calculate moment of inertia of whole body once. I will choose a small part dm having a position vector r and calculate its moment of inertia choosing this unit vector n cap, and then I will integrate whole of this to calculate the moment of inertia of whole body. Normally for continuous bodies, if rho is the density, then mass element dm is equal to rho into dv, where dv is the volume of the body. So normally we can write moment of inertia as I n cap is equal to rho n cap cross r square dv. So to find moment of inertia, we need to follow a series of steps, or we can say we need to follow an algorithm. And once this algorithm is clear to you, then you can easily calculate the moment of inertia of any body required. So what are the different steps to to calculate the moment of inertia of bodies. So the number one step is that you have to choose a suitable coordinate system. Why a suitable coordinate system? Because if I need to study moment of inertia of one simple rod, then I can choose my Cartesian coordinate system. Whereas if I want to find the moment of inertia of a ring, then I can choose my plane polar system, as already discussed in classes, having coordinates as r and theta. Whereas if I study 3D and I need to find moment of inertia of a sphere, then I need to choose spherical polar coordinate systems, that is r, theta, phi. So this is how we have to choose our coordinate systems. Number two step is that we have to identify the small element, mass element dm. See, it is necessary because I can find the mass of whole body only and only if dm is known to me with its position vector r. Number 3, I have to calculate the moment of inertia. Mi here is moment of inertia of small element dm using the formula di is equal to dm n cap cross r square. R is a vector here, n cap is also a vector. And then final and last step is that we have to integrate the value to find the moment of inertia over the whole body. So see, it's very simple. I am again just going to discuss the steps. That number 1, you have to choose the coordinate system, whether we have to work in Cartesian system, or we have to work in plane polar system, or we have to work in spherical polar system. Then we have to find a small part of which we have to find the moment of inertia, and we identify that small part along with its position vector. Then we have to find the moment of inertia of that small part, and once we have discovered that, or once we have derived that value, to find the final value, we integrate that di, we integrate this di with this to find I. So our very first problem in this case is that we have to find moment of inertia of thin rod. Okay. So moment of inertia of a thin rod can be found in two ways, because if I consider a thin rod, it can have two axes. One axis which is passing along through the center of the rod and along the axis of a rod, whereas another axis is passing through the center of the rod but perpendicular to the axis of rod. So here in this problem I will be discussing about this part, this axis which is perpendicular to the rod. So studying the moment of inertia in this case, what I do is, I consider a rod of mass, total mass m and total length as L. I choose center as the origin. So the origin, to choose origin is very important because your origin will define the position vector and your origin will define ultimately where your mass element lies. So I choose center of the rod as origin. So because rod is thin, so I consider that rod is lying along x-axis. And remember, I have to find moment of inertia perpendicular axis passing through the center but perpendicular to the axis of rod. So x-axis there are two axes which are perpendicular to x-axis, y-axis or z-axis. So in this case, what I consider is that I consider this perpendicular axis as y-axis and this axis along which rod is lying as x-axis. So here comes my first step, that I have chosen my coordinate system, that is xy axis, and my next step is that I have to identify, because when I choose my suitable coordinate system, this will also define my n cap. So because I have to consider here that axis is passing through the center of the rod and perpendicular to the rod, so here my n cap is j cap. Here my n cap is j cap.